Okay, good morning everybody, and first and foremost, thank you very much for coming. My name is Simon Bingham, and I'm the current chairman of Caunton Engineering. Welcome to our Dissemination Day. There's no fire alarm planned, so if it does go off out the door, across the car park, stand in the right hand corner. That's the only admin we've got room. Toilet just down to the right. Just very briefly on this project, we ought to sort of acknowledge the funding we've had from Innovate UK, and also from the team's point of view, we've been the lead industrial partner. The STR with Bassam here has been the lead academic partner on this, and the mentoring we've had and throughout from Innovate has been really helped the team deliver what we believe is a very successful R&D project. We've all got the programme for today, really. A series of presentations interspersed with a video that outlines the journey we've been on in terms of testing and trialling and application of how we've built what we've built. And then we've got all the samples across the road and the final build that we can all walk over and have a look at. So you will see physically we've kept all the samples that we made. So you will see things that haven't worked, and you'll hopefully understand why we've ended up where we've ended up with connections, well detailed, and ways of working. So the whole history of the project, warts and all, you'll get to have a kick of tires after we've had some presentations. So without further ado, I will ask Bassam to come up and deliver his presentation, which really outlines the project from a technical point of view. Okay? And if we can get the technology to work. Right, it's all yours now.
Thanks, Simon. Good morning, everyone. This project was really about buildability of double-skin composite construction. So it's not about developing design rules, which is what SCI is generally known for. It's not about structural analysis. It is mainly about how you build these structures. Just to make sure that we know what we're talking about here, double-skin composite construction in its most basic form is two steel plates, shear studs welded to the plates, and the concrete infill between them. And the advantages of this type of construction have been recognized for a long time from the point of view of structural efficiency. What's always been a problem is how you build them, because you have two floppy steel plates. They're difficult to move around. You're going to pour concrete to a reasonable head between them, so that's going to push them. So you need to provide some support or to tie them together in some way. And these sorts of difficulties have probably been one of the main reasons that has inhibited their use. The nuclear industry, a number of years ago, got very interested in this, because if you look at the build program and budget for any nuclear project, they always run way over time, they always run way over budget. And one of the reasons, at least, is that they rely heavily on on-site construction. So they're interested in this because it's possible to move a lot of the civil structural activity off-site and to do more activities in parallel. And the idea is to build less like this and more like this. Another advantage in the nuclear context, but also generally in industrial application, is the dreaded embedded plates. They never end up where you want them because things are not frozen early enough. They are very difficult to put in. I understand on a typical nuclear project there is somewhere in the order of 90 to 100,000 of these. And when you look at the density of reinforcement, even when you do them at the right time, it's very difficult to thread the bars between the reinforcement because of the density of reinforcement. So an advantage of having steel plates on the surface is that you can attach directly to the steel plates, and you can get rid of the embedded plates. And if you need to spread the load, you can use patch plates, you can use all sorts of much simpler solutions than what you have here. And it's not new, although the recent interest has been from the nuclear industry, it has been used in other applications. The picture at the top in the middle is a bridge in Japan where they wanted to achieve a very shallow deck for the span, and this type of construction has a high stiffness to weight ratio. The core walls you see on the right-hand side, these are in the UK, and this is where the double skin composite has been used for the core walls to speed up construction. And the two pictures at the bottom show a comparison of SC and reinforced concrete subjected to explosive charges. And again, there's an advantage there because you have the plate containing the concrete. You don't get fragments flying off as a result of being hit by a charge. The concrete between the plates, once you take them apart, actually almost completely pulverizes, but it remains contained between the plates. So, as I said, the problem has been how you build this, and company Modular Walling Systems developed a concept which looked very interesting to achieve this form of construction, which Caunton Engineering have christened SteelBricks. And this is what it looks like. So it's made out of a plate that is bent. So the joint, the connection between the two plates is integral to the system. And the hole you see there is to allow the concrete to flow between units. So you join several of these together and stretch it out of the screen, and you've got a wall module where you've got the connection between the two plates, you've got the holes for the concrete to flow so you can concrete it. So this is the system that was the subject of the work in this project, and it was to look at how can you build out of this, how easy is it, what the problems are, and so on. But in order to do it, we wanted to base the construction on something real and ideally related to the nuclear sector. And so we looked around for an example out of the nuclear sector, and this is what we homed in on. This is a diesel generator building. There's 58 of these being built in France on the EDF nuclear power sites, and it's a post-Fukushima safety measure to provide additional power in the event of all other sources of power failing. EDF, I should say, were not part of this project, but I was working with them on another project at the time, and they were kind enough to provide the design detail and specification for this building, which is built in reinforced concrete. What we did was we designed this building for all the load cases and requirements that they are designed for in real life in order to get all the sizes as actual sizes. But we didn't have the budget to build the whole building, so you're not going to see the whole building when you go out to have a look. What we did was we picked one part of the building and we built that, still at full scale. And we tried to make life as difficult as possible for ourselves because we picked a part that had quite a lot of variation, different wall thicknesses framing into one another, and we made life even more difficult by experimenting. So we've not tried to standardize anything. We've experimented with lots of different joint details in order to identify what works best, what's cheapest, what's more costly, etc. At the time when we did the design, the most up-to-date design document that was available, this is 2015, was the American specification, which was written specifically for this form of construction, and it had just been published. And you will hear more about this later on, and one of the contributors to that document is with us. Now, it has a number of minimum requirements for size that would be a starting point for sizing the units. It requires for exterior walls that the minimum thickness is 450 millimeters, interior walls 300 millimeters. It sets limits on steel plate thickness from 6 to 38 millimeters. The minimum yield stress allowed is 350 newtons. Similarly, there are limits for the concrete and limits for the reinforcement ratios. So this is where you need to start in terms of sizing your elements. And if you take this and look at different plate thicknesses and different wall thicknesses, so for an external wall, the minimum is there, and these are in the table, in green, the acceptable reinforcement ratios based on that relationship at the bottom of the screen. And so based on that, for an external wall, what you see behind the red line are the acceptable combinations of wall thickness and plate thickness. You also need to consider at the construction stage the stresses that are applied by the fresh concrete to the plates, because you don't want to either yield or deform the steel plates during concreting. And again, based on an analysis, assuming a concreting height of 4.7 meters, which is the height between floors in the building we're looking at, you get these combinations in green of plate thickness and wall thickness that would work. Another limitation is the slenderness of the steel plate. If you make the steel plate too slender, it buckles. And so there is a formula in the specification that limits the thickness of the plate to the spacing of the shear studs, which anchor the plate back into the concrete. And again, based on that, what's shown in green are the combinations that would work. Now, if we're using a 450 steel brick, it means that for an 8 millimeter plate, if you have two shear studs, you split the 450 into three 150 widths, and that gives you 19, which is less than the 24, so it's acceptable. If you use a 10 millimeter plate, you're splitting it into two, and so again 23 there, so a 10 millimeter plate would work with a 450 brick and a single stud. And the last set of sort of sizing requirements relate to ensuring composite action and preventing what they call interfacial shear. And this turns out to be the most difficult to satisfy, because this is where the shear studs are brought in even more closely together. The idea of it is this requirement that governs the design, and the purpose of this is to ensure that you get composite action and that you fail the steel plate before you fail the studs, because if you fail the shear studs, then you lose the composite action. And so this then reduces the thickness to, if you have a 10 millimeter plate, it reduces the spacing between the studs, to 177 millimeters. So that puts you back into a situation of two studs in a 450 deep steel brick. So based on that, we ended up with this initial size of steel brick. And then pragmatically, we didn't do any structural optimization. We took the holes to be 60% of the depth of the brick, and the spacing of the holes to be half the cell diameter. And then with that initial size, we then carried out a full analysis of the entire building under the various actions that you would analyze it to if you were doing a real design of the building. So we looked at construction loads, operating loads, we looked at thermal actions from temperature variations inside and outside, winter and summer, wind and snow loads, which don't make much of a difference in this case, and we looked at accidental loads, in this case earthquakes, not very severe earthquake loads for this country, 0.25 G is what we took, and explosion loads. This is an external explosion acting on the face of and roof of the building. And then you have to look at the combinations of these loads, and you end up with something of the order of about 60 different load combinations to analyze for and identify the worst case. So this table is a condensed version of the different load cases that you would look at with the different load factors applied to the permanent actions, the variable actions, and the accidental loads. And so with these load combinations, we then built a finite element model of the entire structure, and we analyzed it. We also looked at soil structure interaction for the earthquake loading, and we looked at 4 different soil profiles going from a very soft soil to a very stiff soil. And these are some results from those analyses. Now we've translated, I'm not showing you stresses or strains or anything like that on these figures. We've translated back from the finite element results to a plate thickness. And so these contours show you the plate thickness required for the load condition that we're looking at. So for the accidental limit state, this was the worst load combination. And what this is showing is that the plate thickness you require generally is no more than about 3 millimeters, except for certain areas where it can be up to about 8 millimeters. These are the corresponding results for the ultimate limit state, and here again it's the same type of presentation. You've got certain areas where you need up to 14 millimeters, but these tend to be really localized sort of stress concentration areas. Generally, it's around sort of 7 millimeter thickness required. And then this is the serviceability limit state, and it is probably the least onerous. Again, quite thin plates required fairly generally, and only in some localized areas you need greater thicknesses. Those were thicknesses for the walls. This is what we ended up for the floors. The floors were simply designed to carry the floor loading and construction loads during construction. So they are, in terms of steel bricks, they are 225 deep, and the bricks that were used were 450 wide. And as I said at the beginning, we experimented with a lot of different types of connections. So we looked at connections, and you'll see these when we go and look at the structure outside. Some of them are internally bolted. So you've got bolts. Sorry, this is the externally bolted one. So you've got bolts on the outside. Some were internally bolted, and some were welded. And these are the wall-to-wall module joints. The floor-to-wall joints were bolted, and we looked at one detail that one might use where you want the joint stiffened in order to transmit a certain level of moment, and one where it would be nominally a simple joint. Okay, well that's what was done in this project, and you will shortly see a video that shows the full story from fabrication in the workshop all the way through to construction on site. The other thing I'm going to mention briefly is a European project that we've also just completed with these partners involved in the project. And unlike this one, in this project, what we did was to develop design rules. The Americans have a design specification, the Japanese have a design guide, a design code for this type of construction. The Koreans have one. In Europe, there hasn't been one. And so we've just completed a European design guide, which will be published early next year. As part of that project, we did somewhere around 40 large-scale tests that looked at member behavior, connections, a particular conditions that is relevant to the nuclear industry, an accidental condition where you get a temperature of around 180 degrees for an extended period of time. We did some fire tests, a lot of numerical analysis, and that has led to the design guide. And next year, as well as the guide, we'll be producing a lot of design examples to go with the guide to illustrate its application. That's just the cover and the table of contents. It's fairly comprehensive. And one thing we did in that project was we took the same building that we looked at in this project, and we designed it, but we designed it using a generic form of ST construction. So it's two plates connected by bars. And this shows you a comparison of quantities between the reinforced concrete designs, of which there are many, and the SC construction. And so the obvious ones, you see a huge reduction in formwork. The formwork in the SC case is just for the foundations. There's a reduction in quantity of concrete because we were able to make the walls thinner. A big reduction in reinforcement. Embedded plates are completely eliminated. But of course, now you've got structural steel plates, which you don't have in the concrete version of the building. And the final thing is I looked again at the sizing of the steel brick, this time based on the European design guide, which is not as stringent as the AISC specification. And whereas we had a 450 by 450 by 8, I find that with these initial sizing requirements, I end up with a 400 by 400 by, by 10 in the case of the AISC, by 8 in this case. And also, although the picture shows 4 studs, we actually can get away with a single stud on the steel bricks. And so there is, because the spacing, instead of the 177, if you remember back to the table earlier, under the requirements of the European design guide, the spacing can be just over 200. So for a 400 brick, we can get away with a single stud per brick. If we were forced into 450, then we would be pushed back into having 2 studs. So thank you very much. You want me? I don't know if there's any questions, or do you want to take questions now, or want to wait?
Can you just go back one slide? Back on a 275 grade there. Earlier you mentioned the 350.
That's right.
So are you recommending a lower grade steel bricks now?
Yeah, the American specification specifies a minimum grade of 350 of S355. In the European, and the reason for that is to prevent, if you look at the background to it, it's to prevent yielding of the plate and during concreting.
Yeah.
We've actually opted to say you need to check that in the calculation, depending on whatever grade you're using, to ensure you don't get yielding. But we don't automatically limit you to an S355.
Okay.
You managed to do a sort of cost-benefit analysis of building that structure in bricks as opposed to reinforced concrete?
No, we haven't. I don't know, Simon, if you want to say anything about costs.
No, we've not done that. It wasn't really part of the scope of the project. But now we've come towards the end of it, we're starting to get the numbers filtering through. We've got a good idea that what you'll see across the road, which I think is 450, 450, 355 plates, 275 plates, a lot cheaper, easier to bend and everything. And also going from 10 mil, which we've got across the road, to 8, vastly reduces our weld size. So, and number of weld runs, which is quite important. But all those things across the road, we think that's £4,000 a tonne-ish, erected, but not full of concrete.
How does that compare?
We have no idea because we don't know anything about concrete. So we are in discussion. We're trying to work that out because I think that is the absolute key question. So we need a cost comparison, and then obviously we've got to overlay onto that time saving, and then broaden that out across the whole of the construction sequence from initial design, concept design, detailed design. And once you get on site, then the sort of post-construction elements that come from design that may not have been thought through, or elements have changed. We've not really, we've not done that. We've just got a pretty good idea. We know what it costs us. But again, we've got 64 different variations of things on the final building, which in reality, we've boiled it down to, we know 2 connections that we'd like to go with. So we probably need to factor that in as well. Okay? All right, thanks, Becca. What's the video now? No, we don't do that. So let's just press it again. Okay, so we'll now try and play our video.
Concrete composite is a form of construction made of 2 steel plates with shear studs and a concrete infill between the plates. It can be used to construct panels which, when joined together, form complete modules. SC construction offers many advantages over conventional reinforced concrete, including no temporary formwork, faster construction, greater strength and stiffness, and in industrial applications, electrical and mechanical equipment can be supported on SC structures without having to install embedded plates or concrete expansion anchors. During transportation, lifting and concrete pouring, the 2 plates must be connected together to form a self-supporting unit. To achieve this, bars, ribs or trusses, bolted or welded to both plates, have been used in the past. However, welding between the plates is manual and raises issues of health and safety due to the confined space. The steel brick concept was developed by Modular Walling Systems. It is a new generation of SC construction with an integral connection between the 2 plates. The first step in the manufacturing process is a regular pattern of semicircular cuts separated by straight cuts in a flat steel plate. The resulting strips are brake pressed into right-angled L-shaped elements. Shear studs are welded to the solid leg of the element. A steel brick is made by welding 2 L-shaped parts to form a U-shaped element. The pattern cut into the plates creates circular holes in the base of the U to allow concrete to flow between steel bricks when the panels are concreted. Modules are manufactured by welding steel bricks together using automated submerged arc welding. Base plates and details for water floor and wall-to-wall connections are installed in the fabrication shop, leaving the simplest connections to be made on site. In the case of floors, the steel bricks have holes in both the base of the U and in one of the sides, so that the floor can have a concrete finish by allowing the concrete to rise above the plate. To test the buildability of the steel brick system, a full-scale construction trial was carried out. The structure chosen is part of a building which houses diesel generators used to provide electricity on nuclear power generation sites in the event that other means of electrical power supply fail. It was constructed at full scale out of 18 modules. The maximum module size was dictated by road transport restrictions. Joints between wall modules were detailed to explore a broad range of externally and internally bolted connections, welded connections, and complex joints combining bolting and welding. Bolted floor-to-wall joint details with simple and moment connections were also investigated. This enabled the quickest and most versatile site joining details to be identified. The structure was built on a reinforced concrete strip footing. Connection between the wall modules and the foundations was by holding down bolts. All modules were easy to lift and place at their position in the structure and fitted together well. Both manual and robotic site welding were investigated. This demonstrated that robotic welding resulted in a significant reduction in time to complete a joint. The structure was partially concreted using a highly flowable concrete mix. Following curing, removal of formwork at the wall ends revealed a concrete surface with no voids or defects. The project has enabled an innovative concept to be developed into a new construction product. We now have the confidence that steel bricks can be used for faster construction of core walls in buildings, retaining walls, and for industrial structures, such as in nuclear power plant and small modular reactor buildings.
Okay, so this is a video of putting up the steel was erected in 2 days with pretty much 2 men and 1 crane driver on the tools. These are supplies, so got a good indication of the speed of that construction. That's what we were going to go and have a look at, as well as it's surrounded by samples of various things we've done. That's to show during the project that we can take it down. And there's some interesting examples of how to try and deconstruct these things over there.
So just quickly, how long did it take to fabricate the steel bricks? It's 2 days to erect. So
yeah, well, in we work on an hours per ton basis, so and we sort of dropping on and off it. Then on the top of my head, what you say is it?
It's roughly around
2,000 hours to fabricate. 2,200 hours to fabricate all that. Okay. So we've fabricated all sorts of. We didn't get a sort of good production run, if that makes sense. Generally, when we're doing that steel production, we rationalise it so that the first 2 we might stutter with, and then once we get going, we get going. So we never managed to get down any, get factory rhythm going or come down our cost curve on that. So I'd like to think, we'd be able to do it better, and also introduce, it's pretty standard. You can introduce some fabrication shop robotic welding in that. This is all pretty linear stuff.
The automated out welding, that was done as single passes. You didn't try to do multiple passes on the same panel at the same time.
With the sub-art welding, we put a root run in manually, and then we did multiple passes to the plate fixes. But if we came down to 8 now, we could get it in 1 pass.
Right. I presume
so we're three runs.
Enough of it, you could do multiple passes at the same time once the plant is assembled.
Yeah, I mean, we've basically got, R&D projects. We're running with 1 welding gun, but you could come up and down it. Heat is an issue, and there is a balance between speed and level of deposition. And you think, we'll do it all quickly, but it's not. It's a sort of bit of a black art, really, and we've been through a few iterations. Okay.
Simon, you started to allude to decommissioning of such structures now, and putting aside any radiological issues. Do you see significant benefits from SC construction for the nuclear industry in terms of decommissioning?
Well, from what we've done across the road, I mean, when you've got everything welded up, it's a slightly different animal.
Yeah.
So bolted gives you a bit more options. You'll see across the road, we took 1 piece and just tried to destroy it, and it's obviously too robust for that. We've ended up using sawing with the chains. Diamond chains to saw through the brick. When we've got one across there, this is one of the methods we've come across. It's tough to take apart, but you can't have it tough.
No, that's right.
It's sort of a bit of a difficult one. Yeah. Okay, I'll hand over to Kadir, and then we'll finish on the presentations. Perhaps then there'll be more questions come out before we have a walk across the road. This is all right. Okay.
Good morning, everyone. My name is Kadir Şener, and I'm a postdoc research engineer at Purdue University, working under the guidance of Professor Amit Varma, who was the principal investigator on this project and also on the other projects. He wasn't able to make it. He was supposed to do this talk, but he had commitments at school with coursework, and he also just recently became the director of the structural lab we have, so administrative commitments also. So I'm going to try to fill in for him. I also just came from the US yesterday, had some complications during the flights that delayed, so I'm very happy to be here, but I may sound a little tired, so about that. But so we have done some experimental work for modular walling systems, so I'm going to talk about that. But first, I'd like to give some background about what we have done in the past and how all that work led up to building the design standards in the US. So a little bit background about our laboratory. Purdue University is located about 2 hours south of Chicago. This is a picture from our lab, which is called Bowen Laboratory. It's one of the largest structural engineering labs in the US. We have a very large, strong floor, and at the time that this picture was taken, we had a 3-story building that was subjected to lateral loading. So the lab is relatively new, and it provides all the up-to-date equipment for us to conduct our research there. So starting with some of the prior projects that we were involved in. So for steel composite modular construction type of research, it all started with some funding from Bechtel. It was around $200,000, and this is more on the relatively smaller side. As I'll skim through the slides, you'll see that we had much larger budget projects, but they had their own proprietary seawall design with bolted connections, and the tasks were to conduct some experimental evaluation and numerical modeling and providing some design guidelines for their structure and subjecting it to accident thermal pressure loading. So part of this project, we conducted large-scale testing and developed detailed nonlinear finite element analysis models and provided some design recommendations. And that followed by this big project through, it was through Department of Energy, and it was a series of projects that was for Westinghouse AP1000 plant. And as most of you know, that the AP1000 uses SC construction for their shield building and also their containment internal structure and also their auxiliary building. So we conducted experimenting tests and models and developed some design approaches to support their structures. And all this work was reviewed both by the US NRC and also by the UK's ONR in terms of both technical and QA/QC reviews. That followed by a project from Mitsubishi, their subsidiary MNES, which partnered with URS in the US, which at the time it was called URS, now it's AECOM, for their planned US Advanced Pressurized Water Reactor. And again, for this project, we conducted large-scale testing, modeling, developing design approaches. Since this plant, I think the shield wall is a pre-stress containment vessel, but the internal containment structure and also the primary shield structure that supports the reactor, those are both made from steel plate composite walls. So we did a lot of testing for them also. And this work was again reviewed by the US NRC, and they even came and attended some of the testing in our lab to witness some of those. More recently, we had one project from Department of Energy. We moved on to impactive impulsive behavior. So this was, I think, again funded through US DOE and US NRC, but the money actually came from the Korean nuclear agencies, KHNP and KEPCO. And we conducted some large-scale missile impact tests, and again developed finite element models based on the results, and provided some design approaches for impact impulsive type of loading. And this was again more recently from US DOE. We focused this time on the connections. This was again experimental and numerical wall. So we conducted some wall-to-wall, wall-to-slab type of tests, and we actually didn't it did come up with some generic design, not attached to any of the proprietary designs, but it came up with some generic design so that we can provide some guidelines both to engineers and also to regulators who are reviewing the work. So that was the test of this work. It just previously ended. And then again, this is actually a work that became popular, multi-hazard resilience of nuclear structures. As we all know, after the Fukushima accident, this became a hot topic. So we had several fundings from US DOE, SNERD in China, Shanghai Nuclear Engineering Design Institute, and also the Canadian regulator were interested in these topics. So we conducted these simultaneous mechanical thermal type of testing. And part of these projects, we looked at both steel plate composite and conventional reinforced concrete. And we did one-to-one comparisons with the same reinforcement ratio and looking at the performance of the walls on the same base. And again, this is still ongoing. We just recently completed the reinforced concrete wall tests and working on some FE modeling, and then hopefully we'll end up providing some design guidance on this type of loading cases. And throughout all these projects, we were able to publish more than 30 journal publications and 50 conference publications. We probably averaged 9 to 10 in each SMERT, starting from 19 to 24. And all these publications are available on Dr. Varma's website, so that's the link for it. You're more than welcome to visit it and get more insights about the work we did in the past. And what you'll see there is we covered most of the member test analysis and design by looking at the out of plane, in plane. Now we had cyclic axial compression, looked at combined in plane, out of plane loading, and as I mentioned, missile impact blast testing and accident thermal plus mechanical loading. And these are all member level tests, design and analysis guidelines, but we also did some look at system level behavior by performing some nonlinear analysis of containment internal structures on nuclear islands. So some of that work is also on the website. And I only mentioned the work that we did in the US at Purdue University, but obviously there has been a lot of researchers in other countries, especially in Japan, Korea, China, and also Europe. We heard some about that today also. And so what we did was we went into those publicly available documents, picked up the experimental data and combined with what we have. And using those, we developed some experimental databases, which the goal was to develop these design documents. So a task committee under the roof of American Institute of Steel Construction was formed. Task Committee 12, which is a subcommittee on modular composite construction, which Dr. Varma was a vice chair. Dr. Stewart Gallagher was also a member and a collaborator in this task committee. And through their work, this publication was provided. There was an existing specification for steel safety-related steel structures for nuclear facility. It was ASC N690, and in 2015, the first supplement to that was published, and an appendix just devoted to steel modular construction was published. And in 2017, the second edition is also recently came out. And then this is a design guide that's also developed very recently. I think it's just available. It became available online last month. I brought copies of both the design guide. I only have one copy though, but you can take a look at it if you're interested. But both the design guide and the specification is on the table. This design guide, it's the implementation of the design specification. So as you see the table of contents here, we have some background and then provides minimum requirements for the wall thickness or faceplate slenderness, and then steel anchor, detailing of steel anchor and tie bar. And it also provides approaches for analysis or modeling parameters are also provided, and then moves on to individual strength parameters. And this document also includes some design examples. So it's step by step takes you through the design of an SC wall and also an SC joint connection design. So, and in fact, we're planning on putting together a workshop on this to train engineers and also reviewers to train them on how to use this product. The information about the workshop is also on there's a flyer that I put on the table, so if you are interested, you can take a look at that also. And we're planning on doing the workshop in the first quarter of 2018, so hopefully in a couple of months. Okay, so we talked about the background. Now let's move on to the experimental work. So as you saw from the previous presenter, that if you look at a wall segment, you would realize that the wall is naturally orthotropic because you have the plate running in one direction, so it makes the other direction. So because of the web plate being transversed in the other direction, it's an orthotropic structure. So our objective was to look at the out-of-plane shear and flexural behavior, and because of that nature, we took two beam strips, one vertical and one horizontal, and then performed testing. We were looking at the strength, obviously shear and flexural strength, but at the same time, we were testing the fabrication quality. So the specimens were actually fabricated in this facility and welded together. The modules were put together, even the studs were shot and then shipped directly to us. And only thing left for us to do was to cast the concrete and test the specimens. But at the same time, as we were testing, trying to get the strengths out of these beams, we were at the same time looking at the fabrication quality and robustness of the construction quality. And the last objective was to compare it against the code equations, see if the code equations are applicable to this design. So, as I mentioned, we had two large-scale SC beam tests. This is the first specimen, which we call MWS Type 1. For this specimen, we had the inner plates transversed to the length, and some of the basic dimensions are given on the table on the right. So we had a width and thickness equal to 450 millimeters. We had a steel faceplate thickness, which is also the inner plate thickness, as 10 millimeters. And inner plate spacing was 450, stud spacing was 150, the diameter of the inner plate hole was 270, and that equated to a total reinforcement ratio of 4.44%, and then a shear reinforcement ratio of 0.88%. And you may realize it's a very high number, 0.88% shear reinforcement ratio. That's very high because of having the inner plate being equal thickness with the faceplate. And we wanted to test it to fail it in shear, which was quite hard with this high shear reinforcement ratio. So we went with the lowest aspect ratio, which is the shear span to depth ratio. That's the shear span from load to support, that distance versus the depth. So the lowest we could go was 2.0. We didn't want to go anywhere below that because then you would have these D region actions, building arch actions or direct transfer between load and support point. So we didn't want to. We still want to have beam behavior. So we went with the lowest possible, which was 2.0, and hoping that we get a shear failure. And steel material was 440 megapascals, and concrete was 30 megapascals on the day of test. This is the second specimen. This time we have the web plates in the longitudinal direction, and I'm also indicating the weld locations on the top. For this specimen, we had twice the width of the previous specimen because we have this core region in between the web plates and the top face plate. So we wanted to capture the confinement effect in that region. So we went with two unit widths instead of one unit width. Other than that, most of the parameters were similar to the first specimen. So the width was 900, but rest of the parameters, again, comparable with the previous specimen. We tested again at 2.0, and the material properties were similar to what we had for the first specimen. Before we discuss the experimental results, I'd like to take a moment and just briefly go over the design equations that we have in the ASC code for both shear strength and flexural strength. First, the shear strength equation is shown here. You see it's a similar approach as ACI 349 or 318, the building code, where the shear strength is summed by the contributions from concrete and steel if you have a spacing less than half of the thickness. So you can sum these two contributions if the spacing is less than that level. But if it's larger than that, then the code allows you to take advantage of the stress and tie effect. So then it becomes the larger of either the compression strut or the steel tie. So by taking that into account, there is the formulation is modified for spacings larger than T/2. And these are the concrete and steel contribution equations. It's again similar to ACI 349. There are some slight modifications in the numbers. We slightly reduced the concrete contribution due to the things we saw in due to size effect in concrete, but the way it's set up is very similar. Again, the steel contribution is either the tie or the concrete compression strut, lower of the two. And then for flexural strength, it's the simple equation that we developed. It's assuming a force couple that's occurring about 90% of the section thickness away from each other. And for sections that also have this steel faceplate stiffeners, then so for MWS type 2, we had the inner plate in the longitudinal direction, right? So in flexure, the inner plate also contributes for bending. And to account for that flexural contribution of the inner plates, or what we call the faceplate stiffeners, there is this longer equation that's provided in the appendix to have better estimates on the strength. Okay, now we're going to talk about the experimental results. Before that, I'll just go over the sensor layout real quick. So we had displacement sensors located under the specimen, and we had inclinometer sensors that are measuring rotations under the load point and over the supports. And then we also had strain gauges on the steel, face plates, and also on the bed plates. So I just numbered the ones that we're going to discuss in the experimental results. This is the load displacement response for the type 1 specimen. You see a initial linear response, and then we had some nonlinearity as we had shear cracks towards the peak point, and then a sudden failure. It was a brittle failure mode due to concrete crashing. We had this experimental strength was about 800 kilonewtons, and if you compare with the code equation, which for this case you take the larger of the either the concrete or steel, because the spacing is larger than T/2. The shear reinforcement spacing is equal to T, so you take the larger, and if you do that, we get with 743 kilonewtons. So the experimental strength was larger than the code calculated strength. And this plot, we're looking at the moment curvature response, and we obtained the curvature through the rotations that we measured under the load point. Since we have a constant moment region in between the load points, we can assume constant curvature in that region, and estimating the curvature by dividing the rotation by the distance in between the sensors. And that's how we obtain the curvature, and then the maximum midspan moment is plotted on the y-axis. And we also compared this with our 2D fiber model. So what we did was just did a basic section analysis, assuming that there is full strain compatibility between steel and concrete, no slip in between layers. And when we compare, that's the red line there, and it's almost a perfect match. So we had full composite action for this beam. Now we're going to look at the strains First, looking at the faceplate strains S5 and S6. So this is the strain profile that we developed by connecting. This is the top faceplate strain, that's in negative, bottom faceplate strain, that's in positive, and different load levels. We looked at the strain. You see the neutral axis remaining at the same location, about 1/3 of the section thickness, and the strength was 800 kilonewtons. And when we looked at the strains on the faceplate, you realize it's less than 2,000 microstrain, and the yield strain was 2,070. So that also indicates that we had shear failure, not any flexural yielding. But when we looked at web plate strains, there we exceeded the yield strain because we had these, and we obviously had shear failure, so we forced the web plates and even caused them to yield, as you see in this figure. This is a picture that we took post-failure. You see a large concrete crashing in that region, and it's the crack. If you follow the crack, it's almost a 45-degree crack. So you can do a strut and tie truss analogy, as I've shown up there. So you have the ties as the web plates, and then compression strut developing in between them. And you remember the inner plate started yielding, right? And these struts, they're anchoring to the ties. So as the tie starts yielding, it's starting to open up. So the strut is becoming weaker and weaker, and it's cracking wider, and it eventually gave up. So that was the experimental behavior for this specimen. And then now let's talk about the type 2 specimen, which we had the web plate longitudinal in the longitudinal direction this time. We had the similar strain gauge sensor layout, so I'm just going to skip that one. But this was the experimental load displacement response. It's slightly different than what we saw for the first specimen, because again, it's going up linear. We had some nonlinearity up there due to cracking, but then we went into this flexural yielding zone because we started yielding the bottom face plate. And we switched to displacement control from this point on, and as we were pushing it further with more displacement, the specimen just failed in shear. The strength was 2,300 kilonewtons, and the code calculated flexural strength, since this specimen also failed in flexural yielding, we compared it with the flexural strength, which is 2144. That's also shown up here. And again, and this equation accounts for the web plate contribution. So the the code was conservatively estimating the strength of the specimen also. And again, we're looking at the moment curvature response. This time, the stiffness is slightly smaller than the 2D section analysis, and that's probably because this time we don't have the inner plates contributing in the interfacial shear. For this specimen, interfacial shear transfer is only relying on the shear stats, which you have to develop the plate in this very short distance. Remember, this specimen has yielded in this region, so you have to develop the plate in this very short distance and only relying on the shear stats, because they probably deformed. That's why we see some partial composite action and not full composite action for this specimen. Looking at the strains first, the faceplate strains at S5 and S6 up to 1,800 kilonewtons. We were in the elastic range. The specimen went up to 2,300, as you saw. And then we started yielding the bottom faceplate in that loading zone. We exceeded the yield strain, and then this time looking at the inner plates. Again, inner plates were also experienced strains that were larger than the yield strain. So we had yielding both in the faceplate, bottom faceplate, and also in the inner web plates. And this is a failure picture from during the failure of the specimen. You also see a difference from the first specimen. Last time we had a 45-degree angle compression strut failure. This time it was more of a crack that's extending from the load point to the support with a slope of 2 to 1. And that was also different than the first specimen because we didn't have the inner plates in place, so it was a different stress mechanism that was forming. And now let's look at the numbers back again. I already mentioned some of these. The first specimen failed in shear. That was the experimental strength. When we compare with the code calculated equation for this specimen, the steel strength governs, and we have an 8% of safety margin when we compare the strength. And you see the flexural strength for the type 1 specimen. It didn't get there because it failed in shear, therefore it went into flexural yielding. But different story for type 2 specimen. We had experimental strength. This time comparing with the flexural design strength, we see an 8% margin, and it failed in flexural shear because both things happening simultaneously. That's what we call this type of failure. And I'm going to talk a little bit. There's a discussion on how we calculate the shear strength for this case. So there are two approaches. Now I'm going to quickly discuss those. So the way the ASC code is set up, it accounts for discrete shear reinforcement elements. And that's what I'm illustrating in the first plot, where you take this net area of the steel and then just lump it into these discrete steel elements. And if you calculate the strength based on that, you would end up with, you use this equation and end up with almost 1,200 kilonewtons. But instead, because this web plate, there's a lot of steel there, and it's almost working as a continuous web plate. So if I say, okay, I'm just going to find the equivalent continuous plate by subtracting the hole sizes. So you remember this plate that was 10 millimeters, and if I subtract the volume of the holes, that would be equivalent to, let's say, 7 millimeter continuous plate. And if I do that approach, then it almost becomes like a W shape, like a steel section. And that way I can calculate the shear strength by just taking account of the web area, 0.6 A web times Fy, and that gives us 1606. And then here I can also add the concrete contribution, which takes us up to 1882. So for this case, since the failure strength was 2300, this approach seems to be more closer to the experimental strength that we observed. So in order to sum up, we tested two beams which were in orthogonal directions, and the major difference between the two was the inner plate orientation, which, as we saw, played some role in the experimental behavior and the response of the specimen, and also the compression stress that formed in the failure angles, crack angles of the failed concrete. And when we compared with the code equation, the specimens exceeded the code expectations. Both specimens were conservatively estimated using the code. And as you saw in the pictures, the failure was always in concrete. We didn't have any failure in the steel. So that also shows us the fabrication quality was excellent, and we didn't have any failures in the welds or any joint regions. And all the failure was governed by the concrete, so the steel fabrication held it up very well. That's the end of my talk, and thanks for your attention.
Thank you very much. We've now sort of got a period of time for any questions and answers that anybody may have on not just Kabir's but Hassan's presentations. So does anybody have any?
Just got one slightly really silly question. I'm not a structural engineer, so clarify that. But what role do the pins play in? So you've got the steel pins as part of the steel brick design. What role do the pins play in maintaining the strength or the stiffness or?
Pins, is it the holes?
Shear
studs. Oh, they provide the interfacial shear between the steel and concrete. You need to tie them together so that they act as one, as a composite member. And to achieve that, you need some anchoring elements to transfer that horizontal shear from concrete infill to steel faceplate.
Okay, so if you're pouring concrete and one of the studs broke or came loose during transportation, what does that do to the structure?
Right. Actually, that's not part of this project, obviously, but we have done testing on bent studs, and we actually found out that it doesn't do much difference. Although I know there are tests in the field that they bend the stud and then make sure it can achieve that much of angle, you know, it sustains the angle. But we have had a project through Westinghouse where they asked us to look at different stud configurations with bent angles that was purposely bent, and looking at the interfacial shear, which we didn't see much difference from the normal case. Somehow they still engage afterwards.
Yeah, because I think one of the presentations was to say you can reduce your studs from 4 down to 1 per segment.
Right.
So if you now only have 1 per segment, this might be a really silly question. And if it broke in every other segment,
No, it's not that redundant anymore. That's what I'm saying.
and 2, what does it do to the overall structure?
When we say 1, this is 1 within the width of
the 400
and also in the other direction. So that 1 repeats all the way along the wall section. So it's not just 1.
No, sure. It's
Yeah.
was about 400 by 400.
That's right. Yes. Yeah. But there is a lot of ductility in these, and quite a bit of redundancy. And when one deforms, it can shed load to the others. So you're not, unless you hugely over-design this, you're not going to get failure as a result of the studs.
Okay, what's actually driving the stud spacing? Is it the local buckling or is it the interspatial shear?
Right. We have a faceplate slenderness. I think there are a couple of checks that you need to do when you're designing for stud spacing. One of them is the faceplate slenderness requirement, which is the buckling of the plate. And there is also the development length, which Dr. Bassam also mentioned, that you need to develop your faceplate, I think, in 3 times of the depth of, in a length that's 3T, you need to develop the length. So that, I think, is the governing case for stud design in the ASC code.
So in the ISC code, you're required to develop the full yield strength of the plate within a length of 3 times the depth of the wall panel. So you have to provide enough shear studs within that. If the depth is 300, say, within a length of 900, you have to provide enough shear studs to develop the full yield strength of the plate.
Yeah.
So the higher, this is why I said when I go to a 275 plate, I can reduce the number of studs significantly, because the higher the yield strength of the plate, the more studs you have to put in.
There is also the compositeness level. I think there were also some studies on achieving full composite as opposed to partial composite, so that may also be a driving force on that 3T value.
Do you use just the one size stud, or do you have different sizes, different wall thicknesses? Is it all based on just the one type of stud?
There are lots of different sizes, but the work we did here was based on one size.
That's standard 19 mil diameter.
That's right, yes.
Yeah, 3/4 inch. That's what we typically use also. But it's the area requirement. You can provide it in any other way.
19 mil diameter and 95 mil. I suppose that the previous question that was getting at, if you did lose a stud in a panel, is there any way you could replace a missing stud other than rejecting the panel? Because there isn't really. Once you've got the panel there, you've really got to be sure the studs are robust.
Right.
You're not going to get back in again.
I mean, they get tested at a certain sampling rate in the factory before they go by bending them.
I would have thought once you've made up your panel, the risk of any damage to the stud is pretty limited unless anything gets within the ends of the panels.
That's right.
So what was the maximum panel length that you made up for this test?
8 meters.
8 meters.
8 meters.
You could go a bit more than that. Right?
Yeah. One of the
3.5 or 4, couldn't you? Something like that.
Yeah, and one of the things that sits behind the whole project was that this is the funding is directed at developing nuclear building technology for SMEs in the UK. And the design and development of this has been done so that you could make this very basic equipment in any fabrication shop in the world, and you start looking at how it's done. And that was one of the underlying factors that sat behind the grant, that it's all right developing something really clever, but if only someone with £80 million of robots can build it, it's never going to be built. Whereas this, you could really tool up and come down the cost curve, but actually if you start moving around the world, where labour costs are significantly lower per hour than they are here, then this is very buildable. And that comes back into transport, that we were limited on the width of a 40-foot wagon driving down the highways of the UK. If you suddenly hit rail or different forms of transport, you could go bigger.
What you do need is a good press brake operator to get it square over joint on the bend.
Absolutely.
When we were looking at the forming them, did you look at Z-shape forms as well as U-shape? Because what you come down to is put a single bend in, easier for handling. What you could theoretically do is form a Z-shape, put studs on to opposite sides and reduce the amount of welds on the shear transfer.
The reason
but handling it would be difficult, I appreciate that.
There is that, but also behind it is we've sort of licensed the technology from modular wall systems, and it's patented technology that does that, and that also leads into why it is what it is. But we found that welding up the two L's then gives us really good tolerance control.
So you've got a bit of adjustment on the two
ends. And when you suddenly, the more you bend steel and warm it up and heat it up and cool it down, it starts to move around a lot. But that actually did allow us to make sure that each individual brick in fabrication was the same. It gave us that adjustment sort of factor.
Has any work been done into stainless steels?
Stainless steels? No,
I
don't. Sorry, go ahead.
We did a test within the European project that I mentioned, where we had a hybrid panel. So we had carbon steel plate on one side and stainless steel on the other side, because that's sometimes a requirement where you've got corrosive environment on one side.
Right.
But the stainless steel plate is more ductile than the carbon steel plate, so if you're designing something to fail in flexure, you've got even more ductility.
Westinghouse used to make one that you could always do well together.